Hello everyone, I'm Reza, founder of the OptimizationCT.com. Welcome to our website. Are you interested in understanding how to improve the transportation system and make them more efficient? This course will provide you with a strong foundation in transportation problem within operation research. Throughout this book, we will explore the basic concept, techniques, and mathematical model used in address the transportation problems. Whether you're a student, a professional looking to expand your skill, or simply curious about the transportation, this course is designed for you. By the end of this course, you will have a clear understanding of the transportation problem and the ability to use optimization techniques to solve the real-world transportation problem. Let's move on a table of content of the discourse. In the minimum cost flow problem, we will explore the finding cheapest ways to transportation goods through a general network. In the second one, we learn how to allocate goods from the different source to different destination while minimizing the transportation good without any intermediate nodes we discuss in this course about this special topic. For solving the transportation problem, we propose a Simplex method for transportation. In third section, we understand a powerful algorithm used to solve the transportation problem step by step with the idea of the Simplex method in the linear programming we discussed earlier. In the section 4, we discover how to handle situation when the supply and demand good do not match perfectly. And in the final section, we explore variation of the additional constraint in the transportation problem and how to solve them effectively. By covering this topic, we will gain a solid understanding of transportation problem and a skill to optimize them efficiently. In the minimum cost flow problem, a general form of the network problem, we want to distribute the same type of product from the factory to the sale market efficiently. We know the quantity of the products produced at each factory and the required quantity at each destination is known and is certain. Instead of sending product directly to the destination, we can send them to distribution center through the intermediate point instead of directly. So here in this network, you can see that the node 2 and node 3 is the intermediate point, and node 1 is the origin, and node 4 and 5 is a destination. However, there are limits on how much can be transported on each transportation line. So this is the transportation line, and this number, which is 4, is the capacity of this line. The objective is to minimize the cost of transportation product while meeting the demand. So let's look at the simple example of the minimum cost flow problem using the diagram here. The nodes are shown are number circle. So node 1 is a 1 in the circle. And the arc are represented by an arrow. So this is the arc from 1 to 3. It's called arc 1, 3. The arc of a specific direction, meaning the material good can transport from one node to another direction on that direction. For instance, we can send the material from node 1 to 3, but we cannot send the material from node 2 from 1. We use the notation ij to indicate the arc going from node I to j. In the diagram above, each arrow represents a path with a specific capacity and cost for transportation. The capacity indicates the maximum amount that can be transported along the path. So consider that this path is 2, 4, and while the cost per unit represents the expense associated with each unit of transport. For example, in arrow 2, 4, the flow can range from 0 to 4 because the capacity is 4. And each unit of passing through the dispense costs $2. The symbol infinity here indicate that there is no limit in the capacity of that particular arc. Moreover, the number in the parentheses next to the circle represent the available supply and required demand at each node. In this diagram, node 1 is a starting point with the supply of 20 units, and node 4 and 5 are the destination that require 5 and 15 units respectively, indicated by negative sign. In the minimum cost problem, our objective is to discover the flow pattern incurring the minimum cost. To formulate this problem as a linear programming model, let's consider the following notation. Xij, let's represent the quantity of unit transport from node I to j using arc ij. This is the main variable that we use in this problem. Now let's present the linear program model for minimum cost flow problem. So equation 1 to 5 represent the flow balance equation in the network. Let's consider the balance equation in node 1 as an example. Equation state this equation. The equation states that the combined flow leaving node I, which is arrow 1, 2, and 1, 3, should be equal to supply available at node I. So you can see that node 1, 2 arrow leave this node. So x1, 2 plus x1, 3 is equal to 20. This is the balance equation for node 1. This ensures that the outgoing flow match the available supply. Similarly, the balance equation at node 2 indicate that the incoming flow to node 2, so we have one incoming flow to node 2 is equal, which is x12, is equal to its outgoing flow from node 2, so is equal to x24, 23, and 25. This ensures that the flow entering and leaving node is properly balanced. The minimum cost problem is the network that has a unique structure that helps determine the solution algorithm. The flow variable denote Xij balance equation have coefficient 0, +1, and -1. Additionally, this variable appear precisely in two equations. Once with the equation 1 represent the node where the flow origin, here this is +1, x12, this is for node 1, and the ones with the equation -1 here representing the node where our flow enters. So you can see that the node 2 and the flow from arc 1 to enter to node 2. That's why we have the -1. Based on the above characteristic, the general form of minimum cost problem can be expressed as follows. So another one, we have the capacity for arc. You can see as a constraint at the bottom of the model, and we have the objective function we are going to minimize. So this is the cost for each unit of transport passing each arc. So this is a general form of the minimum cost flow problem. The model shown here represents the general form. However, we can simplify this model in the other form that we explain in this presentation. In this presentation, we focus on a special case of the minimum cost flow problem called transportation problem. The transportation problem, which is the main topic of the discourse, is a specific type of minimum cost flow problem that does not involve the intermediate points or nodes. So this is the intermediate. So this is not a transportation. This is a transportation because there is no intermediate point. To express the mathematical formulation of the transportation problem, we define the following parameters. R sub I represent the amount of supply available at source I is equal to 1 to m. Bj represent the amount of demand required at the destination J 1 to M, and Cij denote the transportation cost per unit from source I to destination J, which I is equal to 1 to M and J is equal to 1 to M. In the transportation problem, we assume that the total supply here for our resource is equal to total demand for all destination. This ensures that the balanced distribution for the goods and resource. Suppose that Xij represent the quantity of unit transport from source I to source J. In this case, we can formulate the transportation problem as follows. Here we are going to minimize the objective function, which is the transportation cost, and this is the balance equation for resource I, and this is the balance equation for destination J, and this is the non-negative decon. So as you can see that we don't have any capacity for each arc. Let's see an example. A big company producing its product for 3 factory here, factory 1, 2, and 3, and need to transport them to the 4 warehouse here using a truck. Since the transportation costs are significant expense, the company manager aim to minimize these costs. The table below provide the information about the shipping cost. So you can see that the shipping per unit of transport from 1 to 1, factory 1 to warehouse 1 is 464. And we have the demand and supply. Now, the linear programming model for this problem can be right here. So we have the minimization for the objective function, and this is the balance equation for factory 1, 2, and 3, and this is the balance equation for warehouse 1, 2, 3, 4, and this is the non-negative constraint. So how we can solve this problem? Since the transportation problem is a specific instance of the linear programming, it can be solved using the Simplex methods. However, due to the unique structure of the transportation problem we discussed earlier, the Simplex approach can be utilized to obtain the optimal solution. Instead of employing the Simplex table, the following table can be utilized to save the necessary information we use for solving the Simplex method. So we can see that we have a box here. This is the box for cost of transportation, and this is the box we mentioned here, the reduced cost. So whether a variable is basic or non-basic, we determine the information for the box as follows. Xij is a basic variable, the reduced cost is equal to 0, and the Xij is a non-basic variable. This is the reduced cost. So as you remember, if the variable is basic, the coefficient of that variable in the objective function is 0. So this is that 0, and this is the coefficient of the non-basic variable in the objective function in the row 0. So let's go to the algorithm. In the initial step, we aim to obtain a basic feasible region. In the transportation problem, there are various methods to generate the initial solution. Let's discuss one of these methods here. This is northwest corner rule. The northwest corner rule is a method used to generate the initial feasible solution for the transportation problem. It's based on a simple principle. Starting from the top left corner, northwest corner of the northwest corner of the transportation matrix, we allocate shipment in the greedy manner. So this is the step here. First, we begin the top left cell of the transportation matrix. Allocate. In the second part, allocate the maximum possible amount of unit from the current cell to the corresponding supply and the demand allocation. In the third step, move to the next cell to the right. If the supply in the current row is exhausted, or move down if the demand in the current column is fulfilled. In the fourth step, repeat steps 2 and 3 until the all supply and demand are satisfied. This process continues until the all supply and demand value are used, resulting in an initial feasible solution for the transportation problem. So, what happened in this rule? We first select the variable x11 here as a basic variable, then following this rule, the northwest corner rule, if xij is a current basic variable and the demand from source I is not exhausted, we choose the variable x here, xij plus 1 as a basic variable for the next iteration. However, if the supply from source I is fulfilled, we select xi plus 1j as a basic variable. For instance, consider the simplex table below here for finding the initial basic feasible solution for the northwest corner rule. We start from x11. The maximum value is 30. For 30 and 50, we have the maximum value for improving this initial solution. We modify these two values because the demand is fulfilled here. So we go to the right. We go to the x12. The maximum value is 20 here, and we modify these two values. 20 is to 0 and 20 here is to 0. Because demand and supply are both exhausted, we can move right or down. We move down here and we continue till we satisfy all demand and destination. So this is the initial basic solution with the corner west rule, with the northwest corner rule. So this is the basic initial solution. We start for the algorithm using the simplex methods. The previous method we discussed does not consider the cost, which means it may not result in a solution with the lowest total cost. To address this, the Vogel approximation method is introduced. This method is quite effective and is sometimes used to obtain and approximate optimal solution. Now, how Vogel's approximation work? In the first step, we calculate the difference between the smallest and the second smallest cost for each row and the column that is not yet fully allocated. In the second step, identify the row and the column with the largest difference. In the third step, we select the variable that has the lowest unit cost among those variables in the row or column defined in step 2. In step 4, allocate as many units as possible using the variable, consider supply and demand constraint. And in step 5, we repeat step 1 to 4 until all supply and demand are satisfied. By applying the Vogel approximation method, we can obtain an initial basic solution for the given simplex method while considering the cost. So this is the table we use to find the initial basic solution for the Vogel approximation methods. This is the difference in this column and in this here. You can find the difference between the minimum cost and the second minimum cost. So this is the minimum cost and this is the second minimum cost. We pick the maximum value, this is the maximum value, and choose the cell with the minimum value of cost. So this is the 0 is equal, it is the minimum value. And the minimum value of the demand and the supply here is 13. So we update 13 to 0, 50 is equal to 20, and we remove the column 4, and we have the x44 is equal to 30. And go to the next iteration. In the next iteration, you can see that we don't have the raw 4. So we calculate the difference between the minimum cost and second minimum cost. We pick the maximum value and choose the cell with the minimum value here. And we find the minimum value of the 20 and 16 is equal to 20. So it means we remove in the next iteration row number 4 and update 20 to 0 and 6 is equal to 14. And we continue this process until the demand and the supply are satisfied. So this is the initial basic solution for the transportation problem with the help of the Vogel approximation methods. So let's back to the Simplex methods for the transportation problem. Now we have the initial solution. In the next step, we are talking about the stopping condition. The purpose of the stopping condition is to determine whether the current feasible solution is optimal or not. A feasible basic solution is considered optimal if and only if the following condition holds true for all non-basic variables. So if the Cij minus Ui minus Vj is non-negative, we have the optimal solution. To assess these conditions, the value of the Ui and Yj should be calculated. If the variable Xij is a basic, then Cij is equal to Ui plus Vj. We can calculate the Ui and Vj by solving the equation associated with the basic variable. Because the number of variables is one more than the number of equations is very important point. Finding the solution requires setting the one variable to a desired value, for example 0, and obtain the value of the other variable. So to illustrate this, let's consider the basic variable here x31, x32, x34, x21, x23, x13, x15, and x45. In this case, we have the following equation because these variables are basic. To simplify the explanation, let's assume the u3 is equal to 0, as it appears more frequently in the equation. By doing so, we can determine the value of the remaining variable as follows. So v1, v2, v3, v4, u1, u2, u3 here. So we can calculate u1, u2, u3, u4, and v1, v2, v3, v4, and v5. So this is the optimal value of the dual variable. During the deduce step, we determine the input basic variable and the output basic variable. In the Simplex method for the transportation problem, we choose the variable with the smallest negative value of the Cij minus Ui minus Vj as the input basic variable. Taking into account this variable by the Simplex table as follows. So the red box is the reduce box for the non-basic variable. If the all value are non-negative, the optimal solution is found. In the given table, the variable x25 has the smallest value of Cij minus Ui minus Vj and is chosen as the input variable because it is negative. To determine the basic output variable from the base, we employ the following method. We use the cyclist process to update the flow of the arc. If we add the value, if we add the arc with the flow of the theta, we update the other variable as follows. In this figure, the value of the theta need to be increased to ensure that the cost of the all arc, the flow of the R arc is non-negative. By increasing the value of the theta by 10, we remove the variable x1, 5 from the basic variable, making it the output basic variable. As a result, the updated basic variable is as follows. So if we set the theta is equal to 0, is equal to 10, we have that this is the new basic variable. And we continue the process. Before we proceed with the solving the example using the Simplex method for transportation problem, let's continue with the formal explanation of the Simplex method for the transportation problem. In the initial step, we obtain the initial basic solution using either the northeast corner rule or Vogel approximation method. In the stopping condition, we solve the equation Cij is equal to ui plus vj for the basic variable to determine the value of the ui and vj. If the conditions Cij minus ui minus vj is non-negative hold for all non-basic variable, the current basic solution is optimal. Otherwise, we proceed to the iterative step. We have the three parts in the iterative step. Identify the non-basic variable xij that has the most negative value of the Cij minus ui minus vj as the input basic variable. Determine the output basic variable as a cyclic process. And then calculate the new basic variable. Go back to the stopping condition and repeat the process till the stopping condition satisfied. We talk about some special cases of the transportation problem. When the total supply exceeds the total demand, denote that here we encounter a situation where the additional supply is available. To address this, we introduce a virtual demand node in the transportation table with the demand amount of equal this equation. Since no actual goods are being transported to this virtual node, the transportation costs for each unit are also considered as a 0. When the total demand exceeds the total supply here, we encounter a situation where the additional demand need to be fulfilled. To solve this, we introduce here a virtual row in the transportation table with the capacity is equal to this equation. Since no actual goods are being transported from this virtual point, the transportation costs for each unit of this row are considered as a 0. Solving a non-standard transportation problem have other cases we discussed in this slide. In the transportation algorithm, the basic assumption is that the total supply is equal to total demand. However, in the case where this assumption does not hold, we can modify as we discussed in the earlier slide. There are other non-standard forms for transportation problem to consider. One example is an impossible cell situation where it's extremely difficult to transport goods between a specific origin to a specific destination. This can be due to absence of the direct route of or a significant distance between them. Another non-standard form occurs when the supply capacity at the origin falls within a certain range. In this case, the supply amount is limited between upper bound and lower bound. Similarly, the demand can also have a certain range. This situation is referred to the bounded capacity. In subsequent discussion, we will go into the detail of these standard form and explore how to address it in the solving the transportation problem. We start with the impossible cell. In the real world, there are instances where it's not feasible to transport goods from a specific origin to a specific destination. To deal with this situation, the transportation problem, we assign a cost value of m to the corresponding cell in this transportation table. Here, m represents a large number that show the cost of the transportation of the single unit of goods. In the transportation method, cell with the cost the value of m are left unassigned because the objective function is going to minimize the cost. Consequently, the variable associated with such a cell remain non-basic in the final table. This approach ensures that the algorithm focuses on finding the most cost-effective route while disregarding the impossible ones. Let's consider the transportation problem involving an origin that has a specific capacity limitation, which is called bounded capacity. For instance, suppose the first factory has a flexibility to increase its capacity by implementing second or third shift, or even decrease it when it's necessary. Taking this situation, the initial capacity of the first factory without additional shifts serve as a lower bound. Let's introduce a modified table that accounts for upper bound of the capacity in the case of the new production line 1-2 here. The lower bound remains the same as the main capacity without any additional shift. However, the upper bound reflects the previous cost value and the supply amount correspond to the difference between this upper and lower bound, which is 200 in this case. Incorporating a new source increase the supply beyond the demand and required inclusion of a virtual node. It's important to note that the virtual cell in row 1 is considered impossible and is assigned a cost value of m. This ensures that the supply node 1 maintain a minimum capacity of 100. If the cell were not assigned to m here, there would be a possibility of flow from node 1 to a virtual. So this is the arc between 1 and virtual node. Supply node 1 unable to fulfill the demand of node 1, 2, 3, 4. So all assigned to arc 1 to m. Hence, the supply node can produce 100 of goods during the first shift and 200 of goods when additional shift line 1, 2 are implemented. So we consider the cost of this arc is m and the other is equal to 0. So by doing this, we guarantee that we have a bounded capacity for origin or supply node. Similar to bounded capacity for supply node, a transportation can be also involve the bounded capacity for demand. For example, let's revisit the previous example without considering an additional shift for supply node 1. Now suppose that the demand for node 1, which is column 1, vary between the range of 100 to 250, meaning that the value of the D1 can be anywhere between this bound. Here, this is the updated table for the new column we consider. The bound for node 1 is set to 100, which is the lower bound of the demand point. Node 1, 2 represent the extra demand beyond the minimum requirement for node 1, which is 150. The transportation cost region to node 1, 2, which is column 1, 2, are the same as the costs of the associated with the reaching node 1, which is column. So this is the transportation cost for both is equal. The demand and the same cost associated with the reaching node 1. The demand for node 1, 2 is calculated as a 200 upper bound minus 100, which is 150. The difference between upper bound and lower bound. To maintain the balance between supply and demand, the virtual node is assigned to capacity of 100. So it's similar to the last slide. It's important to ensure that there is no flow between the destination node 1 and the virtual as discussed before. So if it happens, there is no flow between arc 1 and 1, 2 and 1, and 3 and 1. So it's not impossible. So we should consider the cost of the virtual node to 1 is equal to m, which is a large number of value. To achieve this, the cost corresponding call is set as m. Why m? Well, if a flow were loaded from the virtual node to 1, it would be imply a flow that does not actually exist. So that's not actually exist. This is the virtual node. This would be result in the node 1 and node 1 to sending a total of 150 of units flow, exceeding the lower bound. Moreover, there would be a value between the lower bound and upper bound. So it's not impossible to get the value between 100 and 150. If we don't set the cost value of the node, virtual node to 1 is equal to m. By setting the cost of the distal as m, we guarantee that the minimum input for node 1 remain at a unit of 100. Let's examine the transportation problem with the production with the different cost present here. It's too simple. In this scenario, we have a 3 factory with a different production cost. This cost differ due to the factors such as the labor expense, equipment cost, and raw material price. Our objective is to distribute the production output from this factory for among the 4 warehouses in the manner of the minimum in the manner that minimize the total cost of production as well as the transportation. If we assume that the production cost per unit of 3 factories is 50, 62, and the 44 respectively, the total cost will be determined by adding the production cost to the transportation cost for each unit. So here, this is the updated table. As we stated, the production cost for factory 1 is 15. So we add the 19 plus 15 is equal to 69. For factory 2, the production cost is equal to 62. So we add the transportation cost, which is 18 plus production cost, which is 62 is equal to 80. And finally, the production cost for factory number 3 is 54, and the total cost would be 68. This table shows the optimal solution for considering the transportation cost as well as the production cost. Sometimes the products from the same factory can be sold in the various market at a different price. Let's consider the previous example where the distributed product from the 3 factory and 4 warehouse. In this case, the selling price per unit of each warehouse is equal to 100, 105, 110, and 115. To minimize the cost in transportation problem, we incorporate the selling price with a negative sign. This means that the number that inside this small upper bound rectangular represent the difference between the negative selling price per unit and combine the shipping and transportation costs. By considering this value, we can accurately assess the impact of selling price on the overall cost. The objective function here, this is the selling price in destination 1, and this is the selling price for this at warehouse 2, and this is the selling price at warehouse 3. So here, by considering the value, we can accurately set the impact of selling price on the overall cost. So the selling price is as a benefit and the transportation and production cost as a cost. So they should have the different sign. The objective function remains to find optimal distribution that minimizes the total cost, and the price, selling price, we should consider as a minus in the calculating the total cost because the selling price is a profit. Total cost, and so we solve this transportation problem that we consider the transportation cost, production cost, and selling price. Let's note that it's a very important point we should consider. It's important to highlight that the optimal solution in this table remain unchanged from the initial case that we don't have the production cost and selling price. And the case involving a production case, which is the last with a different cost. The addition of the fixed value to the cost in the column or row does not alter the optimal solution, which is very important. So let's solve an example in the transportation problem. A canning company operated factory in the three cities, Chicago, Cleveland, and Boston. During the previous week, the production output of this factory was also 35 units from Chicago, 50 units from the Cleveland, and 40 units from the Boston. Now the company aimed to transport this product from to the four different distribution centers: Dallas, Atlanta, San Francisco, and Philadelphia. The desired quantity to be shipped are 45 units to Dallas, 20 to Atlanta, 30 to San Francisco, and another 30 units to Philadelphia. To determine the cost optimal shipping method, we consider the production and transportation cost between each factory to the distribution center. The table below illustrated this cost. So we have the three factory in Cleveland, Chicago, and Boston, and the four distribution center, which are warehouse, Dallas, Atlanta, San Francisco, and Philadelphia. We have the supply and demand here. How we can solve this problem considering the all cost? So we start with the initial step. In the initial step, we find the initial basic feasible solution. We have the two methods. The first method, the northwest corner method. We start from the x11 and do the following process as we discussed in the course. So this is the initial basic solution for the northwest corner rule with the objective function 1180. So there is another way, Vogel approximation method we use here. As you remember, we calculate the column difference and we pick the column and row difference, and we pick the maximum, and the maximum we find the minimum value and the maximum value we can set from the demand and the supply. So here this is the 13 and we update 13 and 14. We have the 0 and we have the 10 and we add the row column 4 and we go forward to find the initial basic solution using the Vogel approximation method. So in this case, the optimal solution is 1020, which is less than the basic initial solution for north corner way. After comparing the objective function obtained from the northeast corner rule and the Vogel approximation, it becomes evident that the Vogel approximation yields the better objective function for the basic solution. Consequently, the algorithm will adopt the initial solution derived from the Vogel approximation. Since in the stopping condition, we should calculate the reduced cost. Since there are no basic variable with the value of the Cij minus ui minus vj, we calculate as a follow. We just set ui as a u1 as a 0 and calculate the dual variable as a follow. So we have arrived the optimal solution because all reduced costs are positive. This clearly demonstrates that the Vogel approximation method effectively guides us toward the optimal solution. For additional practice, let's consider this initial basic solution. So in the stopping condition, we assume u1 as a 0 and define the value of the dual variable as a follow. So this is the dual value for u and y and v. In the table here, we calculate the reduced cost. We observe that there are two non-basic variables where the Cij is less than 0. Uh, this indicates that the current basic solution is not optimal. So this is 2 minus. We need to seek and improve the solution. To accomplish this, we select x1, 3, and 3, 2. X1, 3 as the basic solution, as the entering basic variable. To accomplish this, we select x1, 3, and we process the identifying the output variable as a follow. So we just add the arc 1, 3 with the flow of theta. So if we add the theta to node number 3, we should decrease the flow from 2 to 3 by theta. And if we decrease the theta from node 2 to hold the balance condition, we should add the theta to arc 1 and go forward. This is the cyclist process, and we can find the theta is the maximum value of theta is equal to 15, and this is the basic solution. X11 is replaced by the non-basic variable x13 in the base. So this is the new basic solution. So in the stopping condition, we set u1 as a 0, and the value of the dual variable can be calculated as a follow. In the following table, you can see that the reduced cost for all non-basic variable, and we have the one negative value. So we add the arc2 to the basic variable, and we do the cyclist process. The maximum value of theta would be equal to 10. So this is the new basic solution. In order to check we reached the optimal solution, we set u1 as a 0, and if we calculate the dual value of the all our nodes, so this is the reduced cost, and we can see that all reduced costs are non-negative, so we reached the optimal solution, and this is the optimal solution of the transportation cost. Okay, thank you so much for joining us in exploring more example and expanding your problem solving skill in transportation problem. Visit our website to access a wide range of problem solving scenario and exercise. By solving this problem, you can enhance your understanding on this topic. Also, thank you so much for watching us. If you are interested, you can, if you have you have any question, you can send an email by optimizationcity@gmail.com, or you can fill the contact form in our website, which is www.optimizationcity.com. Thank you so much, and goodbye for now.